Hello there. We are beginning the numerical integration now, and it's very interesting. It gives you a very nice application of the things that we have learned up to now. So, this is lecture number 22. I have started sharing the slides, and I hope that you can see them. So why do we need to do numerical integration? That could be the first question that one may want to ask, and the need often arises, of course, to compute the definite integrals of a function which has no explicit antiderivative, or the antiderivative is not perhaps very easy to obtain. So this is what we will have to do. We actually saw an example in the very beginning of this theme, that you wanted to compute the length of the sheet that you would need so that you get a corrugated sheet which is 4 feet long. So after all, it boils down to some mathematics, as everything else does, and in this case it boils down to computing some integral. So this is why we need to do this. The basic method involved in the approximation of the integrals is called numerical quadrature. It's called numerical quadrature. And what we would do is that it would use a summation ai f xi for I equal to 0 to n to compute this integral in an approximate way. And of course, we are going to use interpolating polynomials in a big way. I mean, that simply goes without saying. We don't have to say it every now and then, that the function f will be approximated by the interpolating polynomial. We take the integration of the polynomial together with the truncation error, which is given in the formula for the error, and that together will give rise to this summation ai f of xi with the error. So let's see what happens. We select distinct nodes. So we have the interval a to b, and normally x naught is taken to be a, xn is taken to be b, and then x1 up to xn minus 1 are the nodes which are between a and b. So these are the distinct nodes that we select, and then we integrate the Lagrange interpolating polynomial, which is summation f xi lix. Right? So this is the polynomial Pnx, which is going to interpolate your function at these n plus 1 nodes, x0 up to xn. We integrate this polynomial and its truncation error. There is a truncation error in terms of the n plus 1 derivative of your function at some xi x. We don't know what that xi x is, right? So those are the things that we obtain. So we integrate and we obtain the integral fx dx equal to integration of this polynomial Pnx. Remember, the polynomial is given by summation f xi lix. So this is simply going to be integration of summation I going from 1 to n f of xi lix dx plus the error term, which is x minus x naught, x minus x1 all the way up to x minus xn upon n plus 1 factorial and the n plus 1th derivative at some xi x with respect to x. This is what we do. And the first part gives us summation ai f of xi, because f of xi is going to be constant as far as that ith term. What we would do is that we would switch the integral sign and the summation. Once you have taken these integral sign inside, it's the summation I going from 0 to n integral a to b f of xi lix dx. Now this f of xi is a constant as far as the integral is concerned, so that comes out, and what you have is integral a to b lix dx. Okay, so that is computable and that is going to be called ai. And then you have the error term, where you would take again this 1 upon n plus 1 factorial outside and compute the integral of the inside part. So here xi x is inside ab for each x, and ai are the real numbers, which are simply the integrations from a to b of lix dx. So this is the formula we would have. We would then say that our integration is approximated by this finite sum, summation ai f of xi, and the error will then be e f, which is 1 upon n plus 1 factorial integral from a to b product x minus xi f of n plus 1 xi x dx. A very simple thing. Once you have understood what the interpolation does, how the error is written down, all you have to do is to take the integration of those things. Sometimes we may tweak this method slightly. We will come to that. But right now what we do is that we proceed by taking these nodes which are equally spaced, so that whenever we have to compute some difference, say xi minus xi plus 1 or xi plus 1 minus xi, it will simply be an h or minus h. Those are the things that we are going to have. So we will take equally spaced nodes and apply the above formula to the interpolating polynomials. That's the as simple as it is. Meaning, after having done interpolation polynomials, these things may seem like small potatoes for all of us, but they are not that small, as we will see. And the initial ones will give us the trapezoidal rule and the Simpson's rule. So these are the two rules that we will see in today's lecture. The trapezoidal is obtained by taking the two endpoints and joining them by a straight line. So we have x0, which is A, and x1, which is B, because we are only taking two nodes. Therefore, n is 1, and we define h to be the difference B minus A to ease our computations, and use the linear polynomial P1, which interpolates our function on these two nodes, x0, which is less than x1. And we will get the integral a to b fx dx, which is integral x0 to x1, the interpolating polynomial, which you can verify from our earlier formula, plus 1 by 2 integration of this truncation error. Of course, the 1 by 2 that is outside is also part of the truncation error. So you would say that integral a to b fx dx is integral x0 to x1, because x0 is a, x1 is b, p1x dx, and you would have 1 by 2 integral x0 to x1, the double prime of the derivative at xi x, x minus x0, x minus x1. Now we would like to get a nicer form for the error. The computation of the approximation of integral is something that you can always compute. We would like to get a nicer form for the error, and what we do is that we use the mean value theorem for integrals, which I am sure you would have done in your calculus course. So it will tell you that whenever you have such a quantity, then there is a xi which you can use, which will come out. So it would be as if, instead of taking the integral together with this very complicated function, which is the f double prime of xi of x, we don't know what the xi is and so on, but there is a xi such that this whole f double prime xi simply comes out, and you have integral x0 to x1 of the inside part, which is a much simpler integral to compute. Okay, so without the 1 by 2, the remaining error term, its integral, is in fact a simpler looking integral, except now that this single xi is an unknown quantity. But that is much better than having this unknown function xi x and then having to compute the integration of f double prime xi x multiplied by the polynomial x minus x0, x minus x1. Instead of that, this is a much simpler thing. And typically what we will have to do is to compute a bound on these. And to compute bound, it would now be simplest to use just a bound for f double prime on the interval, instead of looking at the bound on the integral, which was the integral of the error term. Okay, so this is our error term without the 1 by 2 has this form, and we then use it to write, we compute the integration, of course, which will be f double prime at some xi, which stays as it is, and the integral of the inside part from x0 to x1, which you can further compute and simplify and get it to be minus h cube by 6 into the second derivative at some xi. Okay, and now let's see the whole formula. So the formula for the integration is this formula, where we have the interpolating polynomial integral from x0 to x1 minus the error form, which is h cube by 6 f double prime xi, but there was a 1 by 2 which was outside, so that 1 by 2 comes and it gives you h cube by 12. And then this further simplifies to x1 minus x naught f of x naught plus f of x1, the integral, and then by putting the values of x1 minus the lower limit, which is the x naught. And then we observe that x1 minus x naught is simply h. So our formula becomes very simple. It is simply h by 2 fx naught plus fx1 minus h cube by 12, the fourth derivative at xi. So this is a very simple looking formula at the end, although the derivation has a few non-trivial steps, including the mean value theorem for integration. This is the trapezoidal rule. So why do we call it the trapezoidal rule? That's because whenever you have a function whose values are all positive, so it would be above the x-axis, then you are going to join these 2 points, the value x naught, fx naught and x1, fx1 on the graph, and draw the straight line segment connecting these 2 points, draw 2 verticals, and then you have the x-axis below. So it's the area of that part which is the trapezoid. So then the integral is approximated by the area in a trapezoid. That's why this is called the trapezoidal rule. The picture would look as follows. We have the blue graph of the function y equal to fx, and we have a equal to x naught. So here we have x naught, f of x naught. Here we have b and fb, or x1, f of x1. Then we have joined those 2 points on the graph by a thick black line, which is a slightly slanted line, and then there are those 2 vertical drops from those 2 graph points on the x-axis to complete the bounded region together with the x-axis bounding the whole figure from below. This is the trapezoid, and this area is the approximation to the integral. We see already that the error will be sizable because we are using some of the very basic approximation methods to compute this. Meaning, I think when you have learned the definition of the Riemann integration, then you would have seen that these are the trapezoids which we are going to build and compute the area as the limit of these areas of the summation of the areas of various trapezoids by taking various points, various nodes from A to B. That's what we do. So this is the beginning point of that limiting sequence, and therefore there will be error. So this was about trapezoidal rule. The Simpson's rule. So Simpson's rule, as we can guess, will go from the P1 to P2, interpolating polynomial P1, which was interpolating your function at 2 points. We go from there to the polynomial P2, which is now going to interpolate your function on 3 points. So n is 2, and we call x0 to be a, x1 to be a plus h, and x2 will then be a plus 2h, which has to be b, and therefore h is b minus a upon 2. So x1 is the midpoint, x0 is the left endpoint, and x2 is the right endpoint. And I will just straight away tell you the rule. The rule is integral from x0 to x2 fx dx is h by 3. There is an h by 3 here. For the trapezoidal rule, we had h by 2. So h by 3 fx0 plus 4x1, 4fx1 plus f of x2, and the error is in the order of h power 5. Now this should come as a surprise because the error for the trapezoidal rule was in the order of h cube, where we used degree 1 polynomial, and this is a degree 2 polynomial. So if you just use the interpolating polynomial and compute the integral of the error term, it will give you h power 4. But we have to tweak that method and get this slightly better formula, and that tweaking is somewhat non-trivial. So we will postpone the derivation of this formula. We will not derive this formula right away here in this current lecture, maybe sometime later, because it's going to use some more methods than just interpolating the polynomial P2. Maybe I'll just tell you verbally what it is going to do. What we do is that we look at the the Taylor's formula for your function at the midpoint, which is x1. Okay, so we apply the Taylor's formula and get the formula, get the Taylor formula for the second or the third derivative, and then integrate that Taylor formula. So the Taylor formula is f of x equal to f of x1 plus f of f prime x1 x minus x1 plus f double prime x1 upon 2 x minus x1 square plus f triple prime x1 upon 3 factorial, which is 6 x minus x1 cube, and so on. So that's how, and then the error term is in terms of the fourth derivative. And what we do is then that we integrate this formula. By integrating, the f of x1, which is the constant term, should get you an x, but we treat, instead of x, we put x minus x1 there. So instead of integrating with respect to x, we integrate with respect to d x minus x1. So not dx, but dx minus x1, which is going to give you the same answer ultimately, because you are computing the definite integral. Okay, and then for f double prime, we use the formula from numerical differentiation for the f double prime using the P2. So once you put that formula for f double prime in the Taylor's formula and then compute the integral, we get this integral that helps you get the error term in terms of h power 5 upon 90. All right, so this derivation, which I have just very briefly told you, will be taken up sometime later, maybe perhaps if it is taken to some point in the future, but we will not do it now. Instead, we choose to compute some integrals. So ultimately, we should be able to apply this formulae and compute the integrals. So that's what we do, that we will compute a few integrals with these two formulae, the trapezoidal rule and the Simpson's rule. So what we do is that we fix our interval to be 0 to 2. Our length of the interval is now 2, and use the trapezoidal as well as the Simpson's rule to obtain derivatives of some functions. Okay. Note the formulae. Trapezoidal rule will give you 0 to 2 fx dx to be simply f0 plus f2. Our h is 2 now. And trapezoidal rule says that h by 2 f naught plus f2, which is just f naught plus f2. And the Simpson's rule, which give you h by 3, where h is b minus a by 2. In Simpson's rule, h is half the length of the interval, which is now 1. So indeed it is 1 by 3 f0 plus 4 f1 plus f2. Now, if I put for fx a constant function, we are going to compute these integrals for various functions, but if you put fx equal to a constant function and compute the integral, which is equivalent to saying that you just put fx equal to 1 throughout, and then there is a constant multiple if you have a different constant function. So fx equal to 1 will give you the integral here by the trapezoidal rule to be f naught plus f2, which is equal to 2, because your fx is constant 1. And for fx equal to constant 1, the derivative is anyway equal to 2. So you are going to get the correct value. Further, the Simpson's method will give you that the inside part of this square bracket is 1 plus 4 plus 1. That is 6. You divide by 3, and Simpson's rule also gives you the correct answer. So trapezoidal rule is giving correct answer, Simpson's rule is giving correct answer whenever fx is a constant function. And this should of course not come as a surprise, because the errors are in terms of some derivative. And for constant term, there is no derivative, the derivatives are 0. So there is no surprise really that we are going to get correct answer whenever fx is a constant term. You may also try it out for a linear polynomial and see whether you get the correct answer. Okay, so here we go and compute some examples. So we are going to look at fx. We of course know these examples and we can compute the exact integrals, but we will also give the trapezoidal and Simpson's answers to give you a feeling of these things. So we start with f of x equal to x square. The exact answer is 2.667. It's the integral x cube by 3 from 0 to 2, and so it is 8 by 3, which is 2.666666 or 2.667. Trapezoidal rule gives you the answer to be 4. Whereas Simpson's rule, so x square is the graph will be below the straight line joining those two, and therefore the trapezoid has bigger area than the area which is bound by the curve. Okay, so the trapezoidal answer is much bigger, and Simpson's answer is once again correct because the error is in terms of the fourth derivative, and for x square the fourth derivative is 0. We have x power 4 where the exact answer is 6.4. Trapezoidal rule's answer is hopelessly incorrect, 16. And Simpson's answer is somewhat closer to the exact answer. So clearly, Simpson's method is better, but we need to find maybe slightly better method than the current method of Simpson. X minus 1 inverse, x plus 1 inverse, excuse me. So the correct answer is 1.099. Trapezoidal is not too bad. It's 1.333 and Simpson gives you 1.111. Square root 1 plus x square. So the correct answer is 2.958. We see once again that Simpson is giving you almost the correct answer. That has been possible because we have devised a method of using Simpson's rule, which is going to give you the error in terms of h power 5. So whenever your h is small and then the fourth derivative has come, that is, and then h power 5 is divided by 90, which is not the usual denominator that you will get when you are using only the interpolation formula. Okay, and trapezoid gives you 3.326 sin x. The Simpson's answer is once again very close to the mark. 1.416 is the exact answer. 1.425 is Simpson's answer, and trapezoidal rule gives you 0.909. These, whenever your function gives more curvy graphs, the trapezoidal rule is not going to give you the correct answer. Okay, so if you happen to be lucky and the curvy graph, is symmetric and so on, so the extra area that you get above the trapezoidal top line is equal to the area that is below and so on. If you are lucky in those situations, then the answer may be very close. If your curve of the graph is above the line, then of course you are going to get some error, and a very non-trivial error. And finally, we have this exponential function, which is again going to go below the line. So the trapezoidal answer will be bigger, and we see that it's bigger by a much bigger margin. This is where the relative error will tell you that relative error tells you that the answer for trapezoidal rule is much worse than the answer for some other formulae. For instance, this 1.333 for, so this 1 upon x, 1 plus x behaves in a slightly better way compared to the exponential function as far as the trapezoidal rule is concerned. So this is what we have. We will modify our Simpson's rule by a slight margin. So this is what is called Simpson's 1/3 formula, and then there is a 3/8 formula of Simpson, and there is a grand generalization of these formulae which are called Newton-Cotes formulae. So that's the thing that we are going to discuss in our next lecture. We will also see some examples, and that will close out our discussion on numerical integration. So see you until then, and thank you very much.